just want to make sure people are getting Jupyter Hub spun up. And then as we've been doing throughout the week, cloning the C-ICE tutorials repository, that's c-ice-tutorials. And then the channel for questions is going to be different because there's that other session that's going on at the same time. So the channel where you can ask questions is questions-CICE. And I'm Ellen Buckley. I'm a graduate student at the University of Maryland, and I've been looking at ICET2 data in the summer and looking at the ICET2 response to the melting sea ice surface and kind of looking at ICET2's capability to measure melt ponds on the sea ice surface. So yeah, I'm sure some of you guys probably know more about the data product than I do, and some of you guys are probably better at Python than I am, but hopefully you guys can pick up something from this tutorial. The way that this tutorial is going to work is we have 3 notebooks, ATL03, ATL07, and ATL10. We're going to start in that order, and I'm going to go through ATL03 and ATL07. And if we have time, then Alec is going to get into ATL10. And if not, that could be pushed to tomorrow morning during the advanced topics session. But hopefully we'll have time to go through all that. But I'll pause and make sure I'm going at a good rate. And yeah, if I'm going too fast or anything, you can write that in the questions-CICE channel. And then the helpers for this are Axel and Zhang, and they will be in that channel answering questions, and you guys can speak up if you need me to slow down. Yeah. So, okay, I'm gonna go to my.
Yeah, maybe while you're bringing that up, Ellen, just to say, yeah, if anyone has other questions or things they want to talk about, we can try and put that into the session tomorrow too.
Okay, so once you've cloned the repository, you should have a CICE tutorials folder in your home, in your home directory. Actually, I'm gonna do a little poll right now. If you guys are all set up, do you wanna give me a check yes or X no, just to make sure we're all, and you can do that by going into participants and checking. Okay, so if you guys are having issues, you can write that in the questions channel, but I'll just give another second to see if people can get caught up. I'll go back to this because this is the repository that we're cloning here. Okay, hopefully have some more people caught up. I'm gonna go right into the notebooks folder and starting with ATL03, which is probably the lowest level of data that you will be interested in for studying sea ice. ATL03 is the global geolocated photon height, and it's a very large data set. And if you want more information on it, you can go, there's a great technical references tab on the main NSIDC page for the data product, and that has a lot of resources like the ATBD, the known issues document, and the data dictionary. Those have all been really helpful for this, for me, for like looking to see what different variables mean and stuff like that. This tutorial specifically will just use one file, and I've put that file in a shared folder, so that should work for you guys all to pull from. There are 2 share folders on the home directory. If you guys aren't aware of this, there's the tutorial data, which is the ones that, this is a protected one, so you can't write to it, but this is where we'll be, I put the data for this tutorial in the CICE folder. But then there's also this shared folder, and that's what you guys were writing to yesterday in the HDF5 tutorial. And that one, everyone else has access to. So if you go into that, there's all these other people's folders too. And that is a great way to share data, like external data through within your group projects if you want to use that folder. Just a hint. Okay, so what I'm going to do in this notebook is just go through the ATL03, how I pull it in and what kind of parameters I pull in and how to plot it. There's a little bit of adjustment that you have to do for the along track distance and the time variables. So going to kind of go through that. And then also just showing an example of a weak beam versus a strong beam, just to see the differences and see if you want to use both beams, or maybe just the strong beam is good enough for you guys. Yeah, so this is, like I said, is really high resolution, large data sets. And basically, it's for looking at high resolution features on the surface. And then if you're looking at something in ATL07 and it doesn't make sense and you want to like look at more detail, you can pull up the ATL03 granule that goes with it. Yeah, it's really large and hard to manipulate. So don't recommend using it unless you really want to look at these high resolution features, but that's what I'm doing. So I use it all the time. Right, so starting with importing these modules, you probably recognize most of these, but I'm also using CartoPy to map. I don't know if we've seen that yet. And then Fernando was using this yesterday, the astropy.time time function that helps translate between GPS time and UTC time. And then Alec and I put together this readers Python script that we're pulling in and calling RD. So when I'm pulling a function from that script, it'll be rd.the function name. And when I get to that, I'll open up that script too and go through what I'm actually doing in those functions. So the ATL03 data is in regions, so a 14th of an orbit. There are 14 regions. And I just wanted to show these maps to get an idea of where the regions fall. If you're looking at the Arctic, you'll probably be interested in regions 3, 4, and 5, Antarctic 10, 11, and 12. And in this tutorial, and in the ATL07 tutorial, we're going to be looking at a granule in region 4. And you can tell what region it is in by looking just at the file name. So again, the file name is the data product, and then the date and time here. And then the first 4 numbers of this are the reference ground track. And then the next 2 numbers are the number of times that ground track has been covered. So this is on the 2nd cycle. And this is the region here, 04, and then the release and version. Also note that this is an older release because now release 3 is out as of like last week, I guess, but I didn't change that, so sorry. But yeah, so this particular granule that we're looking at in this tutorial is going to be from February of 2019. So what I first like to do is I've laid out the data location. This is the folder that I was talking about. That is a shared folder. And then this is the file name, and pulling it in with H5Py, just making this the file here. And then looking at one specific variable, which is important because it's the orientation of the satellite. So if it's it switches orientation. And that's important because it determines which beam is weak and which beam is strong. So if it's in forward orientation, the right beams are strong. If it's in backward orientation, the left beams are strong. So I always print that out and make sure I'm using the strong beams for my research. And it's just kind of good to have an idea of which is which. And if it's in orientation 2, that's a transition phase, so don't use that data. Right. So then here I'm specifying which beam we're going to look at. The reader that I use only pulls in one beam at a time, just because it makes more sense to me. And specifying the file name and the beam name. And then this is a function from the reader script. So I'm just going to go into the reader script and show you what this function does. So that is in the notebooks folder. Yeah, so basically when I imported this earlier, it imported all the functions that were in there. And to call any of these functions, I made it so that you can just do rd dot, and then it'll have, and then the function name. So for the get ATL03 one, we're pulling in the basic parameters here. And first making arrays of these, like pulling it out of the HDF5 file, making them arrays, and then putting those arrays in a data frame, a pandas data frame. And then that's what this function returns. So at the bottom, you'll see I organize this into a data frame, and it makes it a clean pandas data frame that you can visualize when this function is run. So the variables of interest here are the heights, the latitudes, and longitudes. Those are pretty self-explanatory. And then the delta time is a variable that's time since the Atlas epoch, and the Atlas epoch is January 1st, 2018. So all of the delta time, that is all in reference to this epoch. So we'll have to convert that to UTC time and make it make sense for us to look at. And then the confidence level is a little bit different because it's not an array, it's a matrix. And the matrix is confidence level associated with each surface type. So for us, we're interested in sea ice. So this is the column 2. But also remember that Python is indexed so that the first column is 0. So we're pulling in the second column and then the confidence levels associated with that column. And that will also be an array because it's just one of those columns. And then this part's a little tricky. The way that the along track distance works for ATL03, there's a parameter that's at the same rate as the photons, and that is a long track distance within a section. I'm going to call them sections because to differentiate between the segments in ATL07. But the ATL03 data is split up into 20-meter sections, and each section will have where it starts, how many photon events are in each section. So this is kind of like a pointer index scheme where you have to correct all of the all of the along track distances for each section. So this is also all available so you guys can look at and kind of digest more later if this is confusing to you, but basically just kind of putting the along track distance at the same rate as the photons and having it all referenced to the distance from the equator. So that's what I'm doing here. And then finally, making a pandas data frame, just calling it DF03, and using a dictionary to create the data frame, where this column, latitudes, is associated with the array that I've pulled in from the HDF5 file, lats, and so on. But yeah, just having the basic information coming from that, and then returning, this is what the function returns here. So that's what's happening. I'm actually gonna run this as we go along. So let me do that. This function takes a second just because, as I said, the data is huge and it takes a second to read in. Okay, now I'm just gonna map the data just to see where it falls. Make sure I know what section I'm looking at. So this is just really basic mapping with CartoPy. The first thing you have to do with CartoPy is create the figure and set the projection for that figure. So I'm setting it as the polar stereographic. And then when I add anything to the plot, I have to make sure I reference which coordinate system that data is in so that it can transform to the map's coordinate system. So here, setting it as north polar stereographic, and then making sure I'm specifying what coordinate system the data that I'm plotting in is when I do the scatter plot on top of it. And so this, I've just plotted the heights here. So these are the heights that I've pulled in from ATL03. And you can see it's cut off at that region 4. So this is just showing region 4. Yeah, so that's just to get an idea of where this data is that we're looking at. How are we doing? Am I going at a good pace? Okay, I don't see any. Okay.
Sorry, I have a quick question actually. When you have the part of the script that is dealing with the along track distance, is that actually correcting the variable distance that happens with measuring sea ice, or is that just doing some smaller correction and we're still going to have to account for that variable distance when we do statistics later? Does that make sense?
I think so. I mean, what I'm doing is this along track distance is just distance along the reference ground track in that coordinate system where if the reference ground track, the center of all 3 beams is X, this variable will tell you how far along it is in X. And then there's another variable that tells you how far along it is in Y. And what the manipulation requires here is just so that because it's not given for every single photon what that along track distance is, I'm just creating that distance for every photon.
Okay, I see. Thank you.
Yeah, I don't know if that really answered your question, but okay. And yeah, I'm gonna plot versus, oh, okay. So first what I'm doing is I'm gonna cut it to a smaller section so we can look at a smaller plot. And the way that I like to do this, I know there's definitely a lot of ways to do this, is just create a little bounding box and then make like a true false array based on making sure all the longitudes are greater than the longitude minimum, the longitudes are less than the longitude max. So this is just a true false, and then putting that in and cutting the data frame. So the resampling the data frame to this bounding box and making that cut version of the data frame here. And then what I was saying about the time, you have to convert it to UTC time, or I mean, that's what I like to do. If you know how to use GPS seconds, you can, or like understand GPS seconds easily, I guess you could leave it. But what you have to do is the delta time is time from the epoch. So pulling in what the epoch is, that is a variable in the file. So you can just pull that in easily. And then add that to the delta time, the delta time variable. And so I'm adding it to the whole column of delta time. And so this result just right here is a full array of all the delta times plus the epoch. And saying that this is in the format of GPS and using this AstroPy time function to translate it to a different time. So I like to look at it in UTC date time. I think Fernando yesterday was doing it in like decimal years or something, but this AstroPy time function is really helpful because it kind of takes in whatever and then puts it out in whatever you want. And it accounts for all kinds of time variations. And then for doing a long track distance within the segment, so instead of having it in all distances from the equator, I wanted to look at just the distance from this little segment. So I'm subtracting all of the along track distance X values from just the first value in this little cut segment, so that we can plot versus distance too. So then here we have a cut data frame. So you can see these indexes don't start at 0, even though you're printing out the head here. The index values still say the same, which is kind of helpful. And then having our variables of interest, the latitudes, longitudes, a long track distance, heights, delta time, confidence, the time that we've converted, and then the along track distance. So I'm gonna plot height versus time. And this is just an easy way to plot things, really basic, matplotlib, plot plt.scatter. And yeah, I'm plotting, the coloring is based on the confidence. So I've made it red and green, with red being the low confidence and background photons, and then green is the medium and high confidence photons. And you can see the medium and high confidence photons are at the surface here. And then there's a lot of background photons, and the lower confidence includes the ridges too, but yeah, and then below the surface is these background and low confidence photons, and there's a lot more there than there are above, and also there's not a lot above the surface right now because this is in February, and also this is in the middle of the night, so it's polar night and very dark. So if this was in the summer, you would see more of these the solar background photons above the surface, but really we're just seeing all these background photons that are from subsurface volume scattering, or like the photons bouncing around in the snow and sea ice before returning up to the satellite. Right, and so just also giving another option of plotting versus a long track distance, which is why I wanted to make that variable, just in case you want to have an idea of how far along the surface this goes. This one goes like 12 kilometers is the region that I've cut out. The same plot, just different x-axis. And then I'm going to zoom in a little bit. And by zooming in, I'm actually just changing the x limits of the plot to look at a smaller section, not resampling it again. Okay, and so this is just what 1 kilometer of data looks like. You can see really strong return from the surface, and then those background photons from below the surface. Yeah. And then finally, just to wrap this one up, because I think we need to focus on ATL07, just wanted to show the difference between the strong beam and the weak beam. So the strong beam, just as a review, the ICET2 has 3 beam pairs, so 6 total beams. And in each beam pair, there's a strong beam and a weak beam that are separated by 90 meters. And the strong beam has an energy level that's 4 times that of the weak beam. And so that's what we'll see when we plot that, the difference between those two. So here, yeah, I'm just pulling in the weak beam, which is the right beam, at the same way that I did before. So pulling it in with this function from the readers, and then cutting it to the same bounding box that I did for the strong beam, and then converting time to UTC and converting a long track distance, making that additional column. And yeah, okay. So once you do that, and then making another pretty simple plot showing the difference between the strong beam and the weak beam. And these are 90 meters apart, so they're not like measuring the same ridges or anything, so you won't expect them to be really highly correlated with like the surface features. But you can see here, there's still like a pretty strong return from the surface in the weak beam, but this might not be as useful if there's like clouds. The weak beam might not have as good of a surface return, where the strong beam might have just good enough so that you can see the surface. And yeah, I just wanted to show that difference. You can probably figure out.
Excuse me, Helen. What is this figure for? Is this track over sea ice or on land? What is the height for?
Yeah, so the heights, that's a good question. The heights in ATL03 are referenced to the WGS84 ellipsoid, and they don't have all of the same corrections that ATL07 does. I'm actually going to go through that. It does have some corrections, but not all of them. So it hasn't been corrected. It's not relative to the mean sea surface. It's not, hasn't been corrected for tides, or for all tides. But Yeah, I'll go into that later because that is kind of not a super meaningful height right now. It's like the height relative to the ellipsoid is what it is.
Thank you.
But yeah, this is sea ice. This has all been sea ice.
Ellen, can I also ask a quick question?
Yeah.
Why, so is like, what would a use case for the weak beam be? If it's more prone to basically like failing in the case of clouds and it's not as strong as, it doesn't give as many returns as the strong beam, like what would be a use for it?
It is just additional data. So if you're looking for more data and higher resolution, I guess the main reason that they have set up this weak beam is for land ice and looking at the slope between the two beams, but that's not really relevant to sea ice. So the reason it's there is for land ice applications, but it can be useful depending on what you're looking at. Like let's say you have a specific feature on the sea ice that you're looking at and the strong beam doesn't go over it, but the weak beam does. You could see if the weak beam is strong enough to show you what you're looking for in that. But yeah, I don't use it. I just wanted to show the difference here.
Yeah, I was going to say, I don't really use it much, but I think we're still trying to figure out its potential use for sea ice.
Yeah, thanks.
Gotcha, thank you.
I'm going to move on to the ATLS7 notebook. Okay, so this is the main sea ice data product, the one that we all want to talk about. And this is sea ice heights. So ATLS7, as Alex said in the intro, was that last week? Or was that, I don't know. Yeah, last week. This uses ATL03 and ATL09, the atmosphere product, to create these sea ice height segments, and each segment is an aggregate of 150 photons, and it can be as small as possible up to 200 meters. So that's the resolution. It's variable, but as low resolution as 200 meters, if that makes sense. And again, the NSIDC is really helpful for having all of these resources in the same place. The data dictionary, the ATBD, which goes through a lot of details of the algorithm, and then known issues of this product. Right, okay, so in this notebook, I hope this is helpful based on what I've been hearing in the project meetings yesterday. We're gonna go through just the basics first, like what the groups are in the HDF5 file and how to pull it in, and then kind of looking at the surface type classification and what parameters go into creating that classification. And then also looking at how the clouds affect the returns. Okay. So importing pretty much the same modules as before. I think the only one I've added here is this scipy.interpolate, this interp1d function, which I'm just using to re-interpolate the ATL07 geophysical corrections to ATL03 to get them in the same vertical datum. But I'll get into that more when I get down there. But yeah, and then also pulling in the readers again, because there's the ATLS7 reader in there. Just a bit about the naming convention of ATLS7. It's a bit different because instead of 14 regions, there's just 2. The Northern Hemisphere is 01 and the Southern Hemisphere is 02. And that is also indicated in the file name. So it'll be ATL07 and then dash whatever region it is. So if we're looking in the Arctic, we're gonna want this hemisphere code 01. And then back to the same naming convention as date, time, the reference ground track. So this is 1307, cycle, and then this is usually where the region code goes, but that's kind of meaningless here. I think it's all just 01 for all of them. Yeah, and then the release and version. Okay. So again, the files that we're using in this one are in that same CICE folder in the tutorials data folder on that's shared. And also looking at just in here, pulling it in the same way and looking at the orientation of the satellite to know which beam is strong and weak. And then I just kind of wanted to go through some of the different groups in ATLS7. So ATLS7 is great because of that, that segment height, but also it has so many statistics that could be useful for your research. And those are all there, and it's organized pretty well into different groups. So there's like the basic group with latitude, longitude, time, and a long track distance. And then the heights one, which will have the heights of each segment, the confidence, segment type, that's the surface type classification parameter that you guys seem to be interested in. The sea surface height flag, which is kind of like a refined and simplified version of the segment type. And then this Gaussian width, which is the distribution of the Gaussian width of the distribution of the photons from the surface. And then in stats, there's a lot more than what I'm saying here, but these are the ones that I'm pulling in for this, in this group, which is in a different folder, is photon rate and the cloud flag apparent surface reflectivity. And then these are the geophysical parameters that I pulled in because they weren't applied to ATL03, but they were applied to ATL07. And I'll need these to be able to compare ATL03 and ATL07. So yeah, that's what the readers function is going to pull in. So like before, specifying the beam and then going to this readers script to use this function, and then the output is a data frame. So just going to quickly go through this. This is a lot less complicated than the ATL03 one. So these are all the things that I just mentioned, all the different variables I just mentioned in their respective groups. And in the same way, I'm pulling them out of the HDF5 file into arrays, and then at the end of this function, using a dictionary to create a pandas data frame, which is what is returned from this function. And again, you guys can look through this more if you're interested in how I did this. Right, so this is the output from that function. We have all these different variables that we're going to look at. And then I'm also going to pull in the ATL03 same track. So this is the 1307 track again, but the ATL03, so that we can compare ATL03 and ATL07. And I'm pulling in the same beam too. So, and using this function that I used in the last notebook. I'm not sure if I read these yet. Yeah, okay. Okay, so now I've pulled in the same beam for ATL03, the same beam and reference ground track for ATL03 and ATL07. So we're gonna compare that. And I'm gonna talk a little bit about the surface type classification. This surface type parameter indicates like what the surface is based on a bunch of different variables. So it goes 0 is cloud covered, 1 is other, which is sea ice, and then 2 through 9 kind of specifies what kind of lead it is based on a decision tree that Alex showed in the presentation. But basically the specular leads are the ones with high photon rates because you have that flat lead, and like a lot of returns come from a specular lead. That's the definition of specular. And the dark leads are those leads that have a lower photon rate but are still classified as leads. So similarly, cutting it to a smaller region, a smaller bounding box here. Going to do that for both the ATL07 data frame and the ATL03 data frame here, just making these quick cuts into the region that I'm interested in. Okay. And so, as I've said, the ATL03 doesn't have all of the geophysical vertical corrections that ATL07 does. So in the process of creating ATL07, they make these extra corrections. And these corrections are stored in the ATL07 geophysical group. And so what I'm doing here is interpolating them to the sampling rate of ATL03 and applying those corrections to ATL03 so that we can compare those with ATL07. And I like looking at the ATL07 vertical datum. I'm converting ATL03 to the ATL07 vertical because that is in reference to the mean sea surface, which makes more sense than looking at what we're looking at in the last notebook where the heights were like 18 meters, which doesn't really make sense. So yeah, that's what I'm doing here. This interp1d was from the scipy.interpolate library. And what this line of code right here is doing is looking at a linear 1D interpolation between the delta time values and the mean sea surface values and making that a function, and doing that for all of the different corrections here. And then applying this to the sampling rate of the ATL03. So applying it to, because I've correlated these, the corrections with the DT variable in the ATL07 data frame, I'm just applying it to these, the delta time variable in this, in the ATL03 data frame. And so here I'm making a new column on the ATL03 data frame, the pandas data frame, just called correction. That is a sum of all these corrections. Again, at the ATL07 rate resampled to ATL03, and just interpolating that so that they are applied at the photon level to every photon. And then making a corrected height by doing the heights from ATL03 minus this correction column that I just created. And so now we have these two new columns. This is obviously erroneous, or like a background photon, but these are more realistic values for sea ice surfaces above the mean sea surface. Okay, so after I've done that, I'm gonna just map where we're looking at. I probably should have done this earlier, but just to show you, I do a lot of my work in the Lincoln Sea, which is right here between Ellesmere Island and Greenland. And yeah, so I've been choosing a lot of tracks that go through the Lincoln Sea. But anyway, this is just a little section of data that I've cut it to that we're gonna keep looking at. And then I wanted to make these subplots showing the relationship between the different variables that go into the surface type classification. So like I said, the surface type classification is basically based on the surface photon rate, the background rate, and kind of like the relationship between, or the ratio between those, and then also the width of the surface photon distribution. So here I'm going to plot the photon rate and the Gaussian width. And that's like, if you fit a curve to the returns from the surface, that's like the width of that curve. And then then I'm going to show what the surface flag or the surface type shows you. So what that surface type parameter is. And then the next step in the algorithm, so this is kind of trying to just go through the algorithm with pictures, because the next step after this surface type classification is refining it to make sure you're picking out specific sea surface heights. So this is to create the sea surface height flag. You refine these instances that have been noted as leads. And so you're looking at the lowest 2%. You're making sure that all these leads fall in the lowest 2%, which is what you would expect because they're lower than the sea ice surface. And yeah, that final step, just make sure that they're really low values before flagging it as a sea surface segment. So that's kind of the idea of going through this, is like going through the algorithm to show how it works. Okay, so I'm gonna plot this. I just made, let's see, 5 different subplots, and each one I just scattered information on and kind of did some cleanup with setting labels and such. But yeah, this is just basic plotting code in here. I'm not like skipping over anything important here. Oh, and then I've highlighted this region where you are seeing that sea surface type. That is a lead. Okay, so in this first one, plotting the photon rate. So it's pretty steady here, but you can see there's a spike here. And I've plotted the ATL segments that have been classified as a lead in blue. Hopefully you can see that well enough, at least on your own screen. But these are here in blue, and you can see that there's definitely a spike in the photon rate here. And that's because there's a lot more photons returned. Well, yeah, more photons returned from a lead than there is from the sea ice surface. So that's one indicator that goes into classifying the leads. And then this isn't as prominent, but in the Gaussian width of the distribution from the photons that are returned from the surface, you can see there's a little bit of a drop here that is indicating that the width you would expect to be, if it's a specular lead, you'd expect a bunch of photons returned at the same time. And that would lead to like a narrow peak in when you're getting returns from the surface. So you're expecting a smaller width for leads because they're flat. Or the specular, yeah, they are usually flat. Okay, and so this shows the surface type classification. Like I said, there are 10 different surface type classifications. This one is the sea ice, so they're all sea ice until we get to this point. And then 3 is like a specular lead, is in the specular lead category. And so all of these segments here that we flagged are specular leads as ATL07 defines it. And then the next step goes into like the revision of this to see if they can be flagged as sea surface heights and used to calculate freeboard in the next product. And so that here we're looking at the sea surface height flag, where 0 is sea ice and 1 is sea surface. And so these ones are in fact in the lowest 2% of data and are flagged as sea surface tie points for the freeboard calculation. Are there any like big questions on that? I'm just gonna browse through the chat really fast. Okay, looks like people are answering questions.
Yeah, I think we're good. Okay.
I'm gonna keep going then. And Alex, sorry, I might use up most of your time.
I'm good.
Briefly gonna look at the impact of clouds on data. So now we're looking at that cloud flag. I'm pulling in a different section here because I wanted to show an area that has a bunch of different cloud flags at once. Well, not at once, but in the same region. So pulling in, this segment is from April, and we're gonna pull in the ATL07 with the readers function. And then just gonna map what we're looking at here. So this is, again, goes through the Lincoln Sea because I like the Lincoln Sea. And this is the cloud flag ranging from 0 to 6 across the Arctic here. And you can see, right, okay, so the cloud flag goes from 0 to 6, with 0 being high confidence clear, 1 is medium confidence clear, 2 is low confidence clear, and then it goes low, medium, high confidence cloudy, and 6 is unknown. So I don't know what that means, unknown. Yeah, and so then I'm just going to zoom into, or like subset it to a smaller region that has a bunch of different cloud flags in the same area to see how that affects different parameters. Right, so that information I just said is right here. Okay. So I've chosen a segment that was kind of in the middle of the Arctic here. Oh, cool, mapped this too. So that's the area that we're looking at, Central Arctic. And then I wanted to compare cloud flag and photon rate variables. And the cloud flag, I think, is based off of the surface photon rate. So like or it's related to it. They're related to each other. So you can see that when you plot, I'm plotting the cloud flag on top, and I'm just showing cloudiness is increasing here on this scale. And then the photon rate below that. So the cloud flag here is going from low confidence clear to high confidence cloudy. So you can see this is like a typical photon rate, maybe a little lower than usual, but yeah, and then it like drops when the cloud flag is increasing. So when it is high confidence cloudy, that's when you see a big drop in photon rate or return photons from the surface, which is what you would expect. And then I just want to show how that affects ATL03 data. So pulling in this same track for ATL03, this again is from April, and cutting it to the same region that we've cut the ATL07 data. And then plotting the same thing that we plotted above, and then also plotting the ATL03 data. So this is what we had before, the cloudiness and then the photon rate. As cloudiness increases, photon rate decreases. That's pretty much what I wanted to show here. And then also you can see, this is a really long section. I think it's like 13 kilometers. But plotting the ATL03 heights, and you can see there's fewer returns from the surface when it gets really cloudy at the end of this region. And also interesting to note, now that it's not polar night, you can see that there's a lot more background photons above the surface as well, compared to the other tracks that we were looking at earlier. I'm just going to zoom in again because I like doing that. Cloudiness increasing from low confidence clear and low confidence cloudy to high confidence cloudy, and seeing the photon rate decrease, and then losing some of these surface returns. So you're not getting as good of a return from the surface here. And that will affect different things like the, if you're not seeing as many surface returns, then the ATL07 segments will be longer because it takes a longer distance to get that 150 photon aggregate, which changes the statistics. But yeah, I just wanted to make that point clear that these things are all related. So I'm done with this notebook, but it looks like we only have 10 minutes. I guess we're supposed to meet back in the main room at 10:15.
Yeah, I was just going to suggest, I mean, since we have the tutorials and we want to record them, and if other people want to see them, just go through, and people want to go over in the other meeting, they should do that. But then we have them recorded, and then people can view them at a later date. Does that sound okay?
So you're suggesting we just keep going?
Yeah, I think so.
Okay. I guess, so I'll take questions from these two notebooks. Actually, I'm going to go into the chat and the questions CI's channel and see if I can answer any more questions, but I'll pass it over to Alec to go through ATL07 or ATL10.
Yeah. Cool. Well, does anyone have questions about that thus far? There's been some good chat on the Slack and the chat here too.
Good. Thanks, guys. Thanks for listening.
Yeah, I think one of the things people pointed out on Slack that I think we're using a release 3 ATL3 granule technically and release 2 ATL7s and 10s. One of the things I wanted to point out there is more and more going forward, those release schedules aren't exactly going to line up. So yeah, it might be that in the future you start to see that maybe one of the products needs more releases because they have more algorithm changes that they need to implement. Whereas some of the other products might actually be pretty stable and they don't want to actually change anything. So they'll just kind of stick with the current release. So it isn't always a case that you need the releases to match up. But yeah, obviously we want to make sure in general that we're using kind of similar input data when we're doing these comparisons. Yeah. I also wanted to quickly say, yeah, I think that readers file, I think there was some problem with people accessing it, but we've kind of just used that similarly to how we used it last year, which is a bit of a dump of potential data readers. So there's a couple of different versions of data reader in there. Yeah, we've generally found that everyone kind of has their own favorite way of reading in data. Some people want something very simple, other people want something a bit more developed. So yeah, I think Ellen's is kind of nice and simple, and there's a slightly more kind of convoluted version of a ATL7 reader in that script as well. Any more questions? Or shall I quickly just run through the ATL10 notebook? Michelle is asking, yeah, about kind of getting the latest release of data. I'm not exactly sure that exists, Michelle. So this idea that, yeah, give us all the latest release. I don't know, maybe Walt knows about that if you're on the line, Walt.
No, it's just that, Ellen, you said that was version 2 and version 3 exists. So I was just wondering, is there a command to just download or you just specify the version and that's it?
Yeah. Well,
and also at the beginning, you just had the files already downloaded. I think that was a tutorial yesterday anyway, but it would have been nice to have the command that, you give the region and then you download all the Atlas files you're interested in for that region. I wonder. I mean, I think we've done that, right? But yeah.
I think I was working with Jessica, who was leading that IcePix tutorial yesterday, and she was, we put together a script that would download all of the files that I used in this tutorial separately if you wanted to work on this on a different machine. So I'll talk to her and see where that is, and I can point you guys towards that too.
Thanks.
Yeah, and Walt's saying in the Slack chat that I think what I said was slightly wrong. So if ATL3 levels up, then all the higher ones automatically level up the version. Whereas if a higher level version levels up, ATL3 doesn't.
Yeah, that's Alex as well. Yeah, that's my understanding. I could be wrong, but I believe, ATL3 is the basis for at least most of the higher level products. So I think if it versions up, everything else, at least eventually, will version up. But there could be improvements to the higher level algorithms beyond just the new ATL3 source.
Yeah. Alessandro is asking about the ATL3 versus 7 plot and lead detection. The flat areas looking like leads but are not classified as such. So maybe they're flat first year ice or leads missed by the algorithm. Yeah, I don't know if you have a comment on that, Ellen. Have you looked at those sections much? In general, I think that ATL7, lead finding algorithm is designed to be conservative. We don't want to kind of misclassify ice as open water. So yeah, sometimes I think you'll see these areas that look kind of like leads and maybe they're refrozen leads, but they might not be designated as open water technically. So definitely something to look out for. And that's the kind of tweaks that are being made still to the algorithm.
To agree with that, the new ICE is not really reflective at all, so very reflective. So the way the algorithm works is looking at these spikes in photon rate, and you're not going to see that over newly formed ice. So maybe that's what that is, but again, it's hard to tell just looking at a bunch of little dots like what exactly the surface is, but that it could be a lead that just doesn't fit those qualifications, or it could be a new sea ice that's flat but doesn't have a high photon rate, and that's why it wasn't flagged as a lead in that example.
Yeah. And there's some of the ones that we're kind of trying to actually get rid of in the release 3 ATL7 release, because we're kind of seeing there are some of these regions which in this case they're not picked up as a lead, but in other times they are, and when we've looked at some of the imagery that we have, it does look like it's a refrozen lead, and we don't want to be including that. So yeah, always a bit tough, but yeah. There's another question about the corrections from ATL7 to 3. Does the ATL3 data have corrections in it, or are they only in the high level data sets? I was just going to say that, yeah, in the presentation, the PowerPoint presentation that I gave on Friday, there's some information about what corrections are applied. So, and I think you have some in your notebooks too, right?
Yeah, and in the ATL3, there's also a group that has the corrections that are applied and the ones that aren't applied, that are kind of leaving you on your own if you do want to apply them. The reason I didn't go that route and apply it straight from ATL3 to ATL3 is because the mean sea surface wasn't there and interpolated for the ATL3 rate, but all the other corrections are. And it will say in the description of the variable, it'll say, this is a correction, but it was not applied to this data set, for the things like the long period equilibrium and the inverted barometer corrections that I applied in this tutorial.
Mm-hmm. Ted is asking in the chat if, since new ice is not so reflective, e.g. like Nihilus, do you see reflections from the ice-water interface, maybe broadening the return photon distribution and making it look lower than a lead? I would say that's an interesting research question. I don't have an answer. Do you know, Alan?
That would be great if someone who is doing that comparison between imagery and ICET2 could figure out that question. That would be an interesting research topic.
I don't know if you can hear me. This is Ted. I asked that because my student and I have been looking at OIB data a lot and referencing to leads, and we've found that thin ice sometimes looks further away than the lead. And have no idea why. And I was thinking that might be it. So I was hoping someone else might have seen that in ICET too, or if anybody's done OIB data and seen the same thing, that'd be great to know.
Yeah, I mean, I was just going to say that, yeah, I've definitely seen that in the IceBridge data as well. And yeah, the IceBridge ATM team have often sent us kind of some weird examples of subsurface scattering in leads, which I still haven't seen a particularly good answer for. And I think then there's been maybe a suggestion that it's like sediment or biology that may be kind of driving that, kind of as you're saying, for Nihilus and Frazzle ice or whatever. So yeah, I don't think I haven't seen a convincing answer to that yet. But
okay.
Definitely an issue for our IceBridge lead elevations.
Yeah, so I don't want to take up any time, but then we had a tough, because it was significant enough, it was difficult to decide what to take as a reference. So do you just take things that are definitely leads?
Yes. Yeah.
Because it's just, yeah. Because then you have this unknown bias, and I wonder if that might exist in ICET too as well.
Yeah. Yeah, and I think I think Ron's talked about this before. I think his opinion is that maybe we're going to find that the ICET2 lead elevations are going to be more reliable than IceBridge potentially, so then maybe the referencing will go the other way around. But yeah,
it could be a waveform thing too, right?
Mm-hmm, mm-hmm. Yeah, and that's kind of why the Icebridge ATM team did release the waveform data set, which is at NSIDC now. And I think that was one of the things they're hoping people will look at. And yeah, maybe improvements to that fitting. So yeah, shall I quickly share my screen then, Ellen, and blitz through this ATL10 notebook?
Yeah.
Okay.
Yeah, I suggest we just go on. How long do you think you take for the ATL?
Yeah, I mean, I think this notebook can kind of stand alone. It really just follows on from what Ellen's talked about. Yeah, so I think just a few minutes.
Let's just go on, and those people who want to go and see the talk, the Johan in the main session in 10:15, can of course do so. Otherwise, we'll just try to finish it as close to 10:15 as possible.
Yeah.
Does that sound okay?
Sure. Okay, so yeah, this notebook, yeah, very similar layout to the ones preceding it. Yeah, it's the same ATL. Is this the same ATL7 granule? Actually, maybe we used a different one, Alan. Let me just check. Okay, this is a different granule.
Yeah, it's different.
Yeah. But yeah, the hope is that this is flexible, so you guys can just read in whatever granule you want. So again, let's just run this whole thing. Let's hope this doesn't crash. Okay, so then yeah, this is again another example of one of these readers. So that is in the readers.py file, but I've just put it in line here just so you can see what's in it. So again, maybe this one has a bit more information. We're reading in things like freeboard now and the sea surface height flag. I think I mentioned in the talk on Friday that a lot of the data from ATL7 are just simply carried straight through to ATL10. So that's why it's often a good data set just to use first. Delta time, yeah, along track distance, again, that's all the same as ATL7. Yeah, so that's all pretty basic. So we use the same approach as the ATL7 notebook for just putting that all into a data frame. Here we're just plotting that data using CartaPy. Yeah, I actually jump into thickness. Yeah, there's some stuff at the end of this notebook that I want to maybe talk about first. So why don't we just quickly, I just want to highlight the stuff, extra stuff that I included at the end of this notebook. So if you guys, maybe you have to run this whole notebook first. Yeah, I'm not going to kind of do this tutorial interactively because I don't have too long anyway. The point I wanted to mention is, or highlight here is why ATL10 might be a bit different to ATL7. And what you'll generally find is that there's just less segments in ATL10. So, you know, the main thing that's happening going from ATL7 to ATL10 is, you know, we find this reference sea surface, as Ellen talked about, and then we just simply difference that reference sea surface from the heights to derive a freeboard. But there are a couple of other things that then happen between 7 and 10. One of them is just some kind of coarse filtering. One of those is reducing the, or increasing the sea ice concentration threshold from 15% in ATL7 up to 50% in ATL10. And that's because of worries about waves in the sea ice. Another filter that's introduced is a coastal mask. So we have to have data that's more than 25 kilometers away from the coast. There's another thing which I wanted to highlight here, which is you see this variable called freeboard quality. And that derives from ATL7, and it's really the quality of that Gaussian that's fit to those heights. So yeah, there was some chat about what exactly that Gaussian is, and it's actually this kind of complicated 2 Gaussian mixture that's fit to that 150 photon distribution. But there's this quality flag that indicates how good that fit is. Low numbers actually indicate it's a good fit. High numbers indicate it's a bad fit. In release 2 data, we only let quality flags less than 4 be included as freeboard estimates, but that's increased up to less than and including 4 in release 3. But I just wanted to kind of show you what I mean by that here. So here I have a section of freeboard data. So I'm showing the freeboard in this top panel here. But this isn't, the colors actually indicate this, what I call this freeboard quality. What we can see is most of those are blue, and that's where the freeboard quality is good. It's like a low value. But some of those colors indicate kind of a worsening of the quality. You can kind of see that in this second panel here. So a lot of those are 1. That's like the best fit. So those heights nicely fit a Gaussian. But the quality flags of 2 and 3 indicate that Gaussian fit is getting worse. If you kind of eyeball that top panel, you'll see that a lot of those bad fits actually come from the higher end of the distributions. And we think some of that is being caused by, rougher surfaces, maybe not fitting a Gaussian as well as the kind of level ice surfaces do. So when you're using ATL10, you can kind of apply your own, or even using ATL7, you can apply your own freeboard quality threshold. And so this is just providing an example of this. So here we're kind of, let me just run that cell. How did that not help? But then what I'm doing here is I'm essentially creating a new array, and I'm setting a kind of stricter freeboard quality. And again, this is just an example of the kind of filtering you could do, but if you wanted to, you could look at other parameters in ATL 7 and 10 and use that to apply stricter filters. And so then this final panel here, I don't know why they're not showing. Maybe I need to run. I'm just going to run this all. I'm just going to wait for that to run. Yeah, where are we? Okay. The bit that takes the most time here is this thickness stuff in the middle. I might have to reorder this notebook a bit. Okay, so, oh, yeah, there we go. So while that's running, I'm just going to go back to what this notebook's really showing, and that's kind of how we can do kind of more science with the data. So what I've tried to do here is build on a notebook that I had last year and show how we can go from a long track freeboard data set to a thickness estimate. So I've included in the utilities script, so utils.py, a few extra functions that might make that easy for you. So one of them is get Warren data. So what that does is it, again, we can have a look at this. Is it basically just assigns the Warren snow depth density, snow depth and density climatology to that data frame. So we basically loop through that given granule and assign, we read what the month is, and then we assign that depth and density estimate to that data frame. So that's what's being done in this cell here. So we can see we've got, in this case, we've got freeboard, our freeboard quality, some other parameters, but then at the end of this data set now we have the snow depth from Warren and the snow density from Warren. So yeah, a pretty nice way of just reading that in. Obviously then to derive thickness, we need to do something a bit more. So I've included just the basic hydrostatic equilibrium equation. Right, so yeah, sorry, this is 2 functions. So this one basically reads in our data frame and then calls this function, which is freeboard to thickness, which is just the one below here. And that's the hydrostatic equilibrium equation, which we apply actually within the function here, a water density and an ice density. Again, you can play around with changing those values if you want. And then we derive thickness based on the inputs of freeboard and snow depth and density. So again, here we decide on what those snow depth and density values are. So these strings here indicate which kind of column of the data set we want to use. And then the out var here indicates kind of what we want to call that thickness estimate. So yeah, when we run this, we then have this new column, which is an ice thickness estimate. So we can see our freeboards on the left and now resultant ice thickness on the right. So yeah, just with a couple of lines there, we can go from freeboard to thickness. I don't know why the figures aren't outputting. Well, anyway, I don't want to spend too long on that. I'll try and figure that out and get back to you guys. The other thing I've done is applied some other snow depths. So there's the Nososym snow model that was developed a couple of years ago in preparation for the launch of ICESat 2. You can find out more about that on the GitHub page. And I've included in this repository the Nososym snow depths that I used from this from the first winter season of data collection, so October 2018, so technically August 2018 to the end of April 2019. And I've included just a couple of functions here to read in that data. So again, if we go to the utils file, we can go to get Nososym, and that simply just reads in this data file and then assigns those snow depth and density estimates to that data frame. And then we use that same function we used before, the get snow and convert to thickness, to then use those new snow depth and density estimates to derive thickness. So now we've got what we should have, snow depth, density, and thickness estimates. I think the reason why some of those are nans is because there isn't no estimates at those specific points. Yeah, I think what I'm doing here is I'm cutting to the middle of the granule, more within the ice pack. And then you can see that we do then have density and snow depth and density estimates from Nososym, and then resultant ice thicknesses. So then we can kind of compare, just eyeballing the thicknesses from Warren and the thicknesses from those Nososym inputs. Yeah, again, I don't know why these plots aren't showing up. It's very strange. But anyway,
I think you need to put the matplotlib inline command after the import block, and then it will work.
So like after.
So the cell 1 after cell 2, then it should work.
Okay.
Maybe. Did for me.
Well, let's maybe not worry about that
detail. Yeah, there you go. Thank you.
Let's address that later and let's try to finish up as soon as we can.
Yeah. So yeah, this is just really just to give you guys some kind of guidance on what you could potentially do with that data. But yeah, that's all I had really. Feel free to get in touch if you have more questions.